Thank you everyone for joining us for the KITP's Fundamentals of Gaseous Halos program. Consistent with the rest of this week, we are covering the question, what roles do non-thermal components play, and how different non-thermal processes impact the dynamics and the behavior of the circumgalactic medium. Today, we will be joined by Ellen Zweibel, a professor at University of Wisconsin. So she'll talk and take us through the hour. We encourage people to put their questions or comments or discussion rather than just in the Zoom channel, which is kind of the Zoom chat, which is kind of the intuitive place to go, to instead go into the Slack application and go into Halo 21 Week 3 non-thermal. That will allow us to kind of preserve those comments and discussions, and you can do threads. So if somebody asks a question and someone else knows the answer during the presentation, they can respond and start a discussion organically there. I will be looking over the relevant comments and discussions in that channel when I'm selecting out questions and themes for our panel discussion that will immediately follow Ellen's presentation. So as I've listed here, we have a panel discussion that will take place the hour after Ellen's presentation, graced by a really excellent team. Aaron Betcher, Phil Hopkins, Yanfei Zhang, Christoph Fromer, and Blakesley Burkhart will all be present. I'm super excited about everyone's take on these topics. And then for those who are really enthusiastic and want to continue the discussion, there was Gwen, Rudy, and Drummond Fielding have set up an after party. It will not be on this Zoom. It will be on a separate Zoom, but the link is in the Halo Turbulence group. So I encourage people to join that, particularly if they are interested in having further discussion on turbulence and its impact on the circumgalactic medium and galactic atmosphere. So just a quick announcement. Tomorrow, we will have an update on featured conversations, including the Halo Turbulence group, and we will have structured discussion for any discussion that we missed this today. This structured discussion are in small groups of 5 to 6 people, so everyone really gets a chance to participate and also meet other participants in the KITP program. And these will have topics suggested on and voted by the audience. So, if you have a pet question, you can add it and hopefully other people upvote it, and then that'll be the question that everyone discusses. And it seems to have worked reasonably well the last couple of weeks. And then tomorrow night we have trivia, which should be super fun. Not necessarily astronomy trivia, just kind of general trivia. It'll just be a fun social event. And it's free and everyone can participate. So, and we're deciding what the prizes are right now. So hopefully there will be some great prizes for the winning team.
Really good prizes.
Really good prizes, yes.
Oh man, oh, you guys are making it.
Okay, so our speaker for today, I am very pleased to announce, is Professor Ellen Zweibel from University of Wisconsin at Madison. Ellen, I don't have enough positive things to say. She's amazing. She's done so much great work in the field, kind of straddling the realm between plasma physics and astrophysics. And cosmic rays have become kind of a la mode in the last few years, especially with the application to the CGM. But Ellen has been working on cosmic rays for almost the last 50 years and has really had some seminal work defining the direction that the field is going. Her earliest papers were on confinement of cosmic rays in the ISM, but she's worked on all of the themes of this week: turbulence, magnetic field dynamics, all sorts of things. And amongst her many accolades and awards, she's also written review papers on the title. So we couldn't think of anyone who was more appropriate to give the presentation today. And notably, she's been involved with KITP in the past. And I found that 20 years ago, she and Eve Ostreicher led a KITP program on astrophysical turbulence. So it seemed appropriate to have her back today to talk about turbulence, as well as cosmic rays, magnetic fields, and the like. So please, I'm really excited to introduce our speaker for today, Ellen Zweibel.
Well, can everybody hear me?
Yes.
Well, thank you, Cameron. So I don't know if any of you know the disruptive comedian Sarah Silverman, but she does have a little routine where she's talking to a kid and she says, "Honey, I'm already proud. All you can do is make me unproud." So Cameron, with your build up, let me proceed. So okay, I'll get rid of this. Okay, so I'm going to continue in the tradition started by Peng, a great talk earlier in the week on talking about non-thermal components of the halo and the CGM. I've worked with many people on aspects of this topic, but the work I'll be talking about today draws especially on the work of this subset of my collaborators. My talk also won't be as fun as Peng's, but I'll do my best. So I want to say a little bit about the context that I'm coming from. So as Cameron said, the role of cosmic rays in star formation feedback has really become interesting lately. And this is for, I think, 3 reasons. One is that because cosmic rays have a relativistic equation of state, their adiabatic cooling is much slower than the cooling of thermal gas, and so they can give a sustained pressure push. In the self-confinement model of cosmic ray transport, they also heat the gas collisionlessly by exciting waves, which are then absorbed by the thermal gas. And finally, they may behave somewhat differently from photons. So, radiation pressure-driven winds have this limitation that the radiation tends to kind of squirt out through low-density holes. But because cosmic rays are confined to a magnetic field, which kind of ties the different phases of the interstellar medium together, this tendency may be somewhat reduced. But there is this kind of looming issue, which is that cosmic ray feedback models overpredict the gamma ray emission that's been detected by Fermi and other instruments. And I think Phil Hopkins and his group, more than anyone, have brought this out. And the only cure really that's been found is that if you assume that cosmic rays diffuse with a diffusion coefficient that's significantly larger than what has been empirically derived for galactic cosmic rays, that seems to be the best way to solve the problem, but there is kind of this tension with local cosmic ray measurements. So that's this sort of looming uncertainty that I'm coming from. So with that as a background, I have kind of a dual agenda here. One is to kind of consider a flow-dominated regime, namely a regime with a strong galactic wind, and ask what that contributes to magnetic fields and cosmic rays in galaxies, the CGM, and the universe at large. And that's going to be kind of a short talk in green for both topics. Actually, there are a couple of papers that you can look at. And then I'm going to pivot over to how cosmic ray hydrodynamics works in multi-phase gas. And by hydrodynamics, I just mean that you treat the cosmic rays as a fluid instead of kinetically particle by particle. And I'm going to focus on bottlenecks, which were alluded to and briefly discussed by Peng on Tuesday, and a somewhat newer development, namely the role of pressure and isotropy instability. And I'm going to expose my possibly muddled set consciousness on this, and be very happy to get your input. And as always, we need to test these theories observationally. So we know that magnetic fields are affected by galactic outflows. Here's a far infrared image of dust polarimetry from the Hawk instrument on Sophia, starburst galaxy M82, and you can see magnetic fields kind of being from a primarily in-plane azimuthal orientation far from the center, they kind of get drawn up in these filaments. And then this is actually the astronomy picture of the day from yesterday. This is NGC 5775 showing synchrotron filaments. So the radial component of the field tends to fall off as 1 over r squared, and the azimuthal component tends to fall off as 1 over r with distance from flux conservation. And what that means is that in a galaxy that starts with a mostly azimuthal field, as disk galaxies seem to have in their planes, a rotating wind will kind of go to a Parker spiral-like configuration and be mostly azimuthal when you get long distances away, and the magnitude of the field will drop. And if you have a microgauss field at 1 kiloparsec, you have 10 to the minus 8, 10 nanogauss at 100 kiloparsecs. What about the cosmic rays? So when cosmic rays are fairly well coupled to the background fluid by scattering from waves, I'll talk more about this later, they obey an energy equation like this. So there's a composite velocity, which is the velocity of the wind in this case, or the fluid velocity, and the alphane speed in the plasma component of the medium. And this just says that if we follow an element of fluid moving with this velocity, that the cosmic ray energy density changes due to 2 effects: the compression or rarefaction of the flow, that's one, and the other is spatial diffusion. And we can evaluate the relative importance of these 2 terms by defining a sort of cosmic ray Reynolds number, which is the ratio of the characteristic diffusion time to the characteristic advection time. So in the case that we'll be interested in, the wind is going to terminate in a shock, and RS is the radius of that shock, and there's a wind velocity, and there's the diffusivity. And if we put in Milky Way type parameters, this number is about 500, which implies that cosmic rays are pretty well coupled to the gas, just an empirical statement. And in that case, the cosmic rays lose energy in the wind. And in the case of highly superalphanic flow, which is probably the most relevant case, the energy density just goes like the 4/3 power of the gas density, which means that the energy of an individual cosmic ray goes down like 1 over r. And so a GeV cosmic ray will become an MEV cosmic ray. And in the absence of anything that revitalizes the cosmic rays, we will be dumping all these MEV cosmic rays into the CGM. And I've not worked on the question of whether this has any observable signature, but that might be an interesting question. If we go to subalphanic flow, then U is basically the alphane speed. And in that case, you can show that the cosmic ray energy density goes like rho to the 2/3. And this is due to energy exchange with waves. Okay. So in the diffusive limit, where RC is the cosmic ray Reynolds number is less than 1, the cosmic rays don't lose energy, but I think that's less likely. I think the cosmic ray Reynolds number is actually pretty large for galactic winds, and that means that cosmic rays lose a lot of energy as they fly out. So can they be revitalized by the wind termination shock? So the wind termination shock, we've learned from the solar system here, is when the dynamical pressure in the wind, which is the dominant form of pressure by the time you get far out in the flow, when that becomes equivalent to the pressure of the ambient medium, which I've written here as the CGM pressure, then there's a shock transition. And so we can solve this relationship for the radius of that termination shock. And it scales like this: the square root of the mass loss rate times the wind velocity divided by the CGM pressure. And this 4 pi here assumes a spherically symmetric wind, but you could put in some other solid angle. Whole thing square root. And if we evaluate this for sort of fiducial numbers, 1 solar mass a year, 500 kilometers a second wind, ambient pressure of 10 to the minus 14 in CGS, then this is about 50 kiloparsecs. So we expect these termination shocks to be 50, 100, 200 kiloparsecs from the parent galaxy. Okay, and the shock velocity is about the same as the wind velocity. And there are two types of shock acceleration that we could consider. One is the sort of classical diffusive, it's become classical diffusive shock acceleration. So here's the shock. Here are magnetic field lines that come into the shock at an angle, and the tangential component gets compressed, so the field lines kind of get refracted, and cosmic rays scatter up and down the field lines. They gain energy when they meet a wave head on, and they lose energy when they catch up to a wave. But because the waves are going at different speeds, basically the speed of the fluid flow, upstream and downstream of the shock, there's a net gain per loop. And so this is first order Fermi acceleration. Peng alluded to second order Fermi acceleration of cosmic rays by turbulence, but this is a much faster process, and it's really been embraced by the cosmic ray community as the main acceleration mechanism for galactic cosmic rays. Because the magnetic field may be almost tangential to the shock due to the different rates at which the azimuthal and radial components of the field decrease, we should consider also a mechanism called shock drift acceleration, which briefly works like this. So this is the plane of the fluid and the magnetic field, and so the motional electric field, V cross V, is perpendicular to the plane of the screen. So in order for particles to pick up energy from that electric field, they have to be drifting out of the screen themselves. So there can be a non-zero V dot E. And this can happen because the magnetic field has a gradient. It's stronger here than it is over here. And so shock drift acceleration has been studied a lot in the solar system. It's also been simulated, and it may be an important process here. For diffusive shock acceleration, there's a sort of maximum rate, and I've written down this formula to show you that it scales with the strength of the magnetic field and the square of the speed of the shock. This limit is derived assuming that the waves are nonlinear. The amplitude of the fluctuations is the same as the amplitude of the background field, the so-called Bohm diffusion. And this is plenty fast enough if you have a wind that endures for 100 or even 10 megayears to boost cosmic rays back up to GeV or tens of GeV energy. So I think there's plenty of opportunity for revitalization of the cosmic ray pool. And that was the subject of Chad's paper. So this is the Bustard et al. 2017. And here on the left is, so this is a very simple set of models, just thermally driven. The cosmic rays are, we can just think of them as test particles. And because this is such a simple model, it's possible to run it thousands or tens of thousands of times. And here are the cosmic ray luminosities as functions of mass loss rate and asymptotic wind velocity. So the Milky Way is probably down somewhere over here, where the luminosity is almost 10 to the 40th ergs. But you know, for a very fast wind or very high mass loss rate, you could, in principle, get a very large cosmic ray luminosity. And because the cosmic ray Reynolds number in the flow is very large, the cosmic rays have a very hard time making it back to the galaxy. Most of them just go pouring out into the ambient medium, the CGM or the IGM, whatever it is. So if the efficiency of cosmic ray acceleration at the galactic wind termination shock is what we think it is for galactic supernova remnants, which is about 10%, you could have 10% of the wind luminosity coming out in the form of cosmic rays. Okay, so here's a summary of my claims. So in the flow-dominated strong galactic wind regime, magnetic field is weakened, tends to become azimuthal. the cosmic rays lose energy by adiabatic expansion, but they can be revitalized at the termination shock, which is about 100 kiloparsecs of order, 100 kiloparsecs from the center of the galaxy. And if this doesn't happen, then the CGM is inundated by a flux of exhausted old cosmic ray particles of MeV energies. So one disadvantage of giving this talk over Zoom is that I have no idea. I have no idea if anybody has any questions or if this whole thing was comprehensible. So would anyone like to give me some feedback before we move on to the next part of the talk?
I think it was great, but I'll leave it to our audience in case there are intermediate questions or clarification.
Can I ask a question?
Hi, Daniel, sure.
Yeah, so you mentioned this 100 kiloparsec scales, but that also depends on the star formation history. If you have star burst, which is not very old, then potentially I assume you could have terminal shock way smaller, with smaller radius than the 100 kiloparsecs, right?
Yeah, that's right. And actually, with a very talented undergraduate, we working with Chad and me, we ran kind of a series of bursty models, and the idea was to see if you could, where do shocks form? Can you get interactions between shocks the way you do in the solar wind? And we never actually finished that, but I think it's a very interesting problem, and I think that these winds are highly structured, and episodic star formation certainly drives that. So I can't add much to your question other than say that I think it's very interesting.
Thank you.
Hi, Ellen. This is Chris.
Hi, Chris.
All right. Yeah, I was just wondering if you think that the galaxy has a cosmic ray driven wind. How do you account for the fact that most of the H1 that we see in the halo is falling in?
Yeah, that's a good question. So back in 2008, with John Everett, a postdoc, we attempted to fit the soft X-ray data from the inner galaxy. And it previously, people had tried to fit it as a kind of a hydrostatic ball. And the fit didn't really work very well, but we did get good fits and eventually fitted the synchrotron radiation too, with a rather restricted wind, which I think in the end, we thought that the wind would come from kind of the 3 kiloparsec molecular ring where there's a lot of star formation. I don't think that there can be a wind from the solar neighborhood. The cosmic ray data is also not very compatible with that. But I think there is some evidence for a wind, or it's compatible certainly with some observations, a sort of a thick annular wind that comes from the molecular ring. It can't go too far in because the galactic potential well is too deep. But, we did get good fits to the synchrotron and soft X-ray data in the inner galaxy.
Thank you.
Okay. We can come back to that if you want. Okay. So now, yeah. Is there another, another question?
Hi. Great talk. I just thought it might be helpful to clarify what the implications of for observables would be for a flood of MEV cosmic rays versus GeV cosmic rays.
I would love to think about that. It seems to me that at some level it would become a problem, but I think quantifying that, which approximately might not be that hard. I would love to know more about that. Okay, so now I want to talk about the bottleneck story, and this is related to the whole question of cosmic ray confinement and how cosmic rays interact in multi-phase winds. So I'm going to go through a very sort of short verbal recap of the basic model. So when the cosmic ray scattering mean free path is short, then we treat the cosmic rays as a fluid, just like they were a gas, short mean free path. And the scattering agents, the most important scattering agents, are short wavelength MHD waves, mostly Alfvén waves. And the most effective form of scattering is so-called gyro resonance scattering. And in gyro resonance scattering, particles travel one wavelength of the wave in the time it takes them to do one gyro orbit. So that's gyro resonance. And if the waves are generated by the cosmic rays themselves from this streaming instability, which I'll keep alluding to, that is the self-confinement model. But if the waves are there for some other reason, like a turbulent cascade, then they're extrinsic confinement. And I'm going to assume, at least for the first part, that we have self-confinement by the streaming instability. Okay, so the cosmic rays stream down their pressure gradient. That's intuitive. And the streaming instability will excite waves. So an Alfvén wave, it propagates up or down the field line. And if we think of it as an electromagnetic wave, which it is, it can be left or right circularly polarized. And so drifting or streaming will excite waves which are propagating in the same direction as the streaming, and both circular polarizations are excited. And cosmic rays, so even though there's a bulk drift, it's very small compared to the individual random motions of cosmic rays. And cosmic rays going one way will gyroresonantly scatter from one circular polarization, and cosmic rays going the other way will scatter from the other circular polarization. So when you have waves propagating in just one direction, it's necessary to have both circular polarizations to be able to scatter the cosmic rays, or put another way, linearly polarized waves. Okay. Now, when the coupling is strong, limit a really short mean free path, the cosmic ray pressure varies with the gas density as the 2/3 power of the gas density. This assumes that the cosmic rays have an ultra-relativistic gamma equals 4/3 equation of state. And John Skilling, one of the early pioneers in this field, who then went into maximum entropy, pointed out back in 1971 that this picture kind of carries the seeds of its own destruction if the gradients of cosmic ray pressure and density become anti-aligned. So as long as cosmic rays are streaming down their pressure gradient, and that's also down the density gradient, everything is fine. But we reach a paradox if the gas density begins to increase along the flux tube. And that's because then the Alfvén speed goes down, the cosmic ray pressure goes up, and then you have the cosmic rays streaming up their pressure gradient, and that doesn't make sense. And faced with this irreconcilable contradiction, cosmic rays just kind of decouple. And I'll show you, so the first person to show this in a computation was Josh Wiener as a graduate student working with Peng. So we're going to consider this very simple problem of what happens when we have a cosmic ray source that's magnetically connected to a cloud. We're going to initially assume that everything is fully ionized, and let's just kind of see what happens. So Josh did a 1D calculation, and so you turn on the source, and here is the cosmic ray energy density at various times. So you can see that initially there's this front that kind of moves out, and when 6 megayears, which is about the Alfvén travel time to the cloud in, with the setup assumed, we get this kind of flat, steady state gradient. And I guess this isn't too visible, but this basically shows that the predicted invariant is indeed invariant, namely that the cosmic ray energy density goes as the gas density to the 2/3 power. This is when you have no cloud. Okay, now here's what happens when you put in a little toy cloud. So there's this density enhancement and concomitant dip in the alphane speed. And now, as you can see that the cosmic ray pressure is increasing. So the cloud is here. And between the source and the density maximum, the cosmic ray pressure is essentially flat. So this was the first numerical demonstration of a bottleneck. Now, this cosmic ray pressure does a couple of things. So when the cosmic rays reach this point here, the cloud maximum, they re-engage, and you get this VA.grad P cosmic ray heating of the cloud, which kind of ablates it. And also there's this pressure built up behind, and something that we didn't appreciate initially, but came to recognize later, is that when you turn on the cosmic ray source, you create an acoustic pulse, which, if the sound speed is greater than the alphane speed, actually makes it to the cloud before the cosmic rays themselves do, and that gives the cloud a push. And what the cosmic rays tend to do is stretch the cloud out, and they can also set it into motion. So if you assume that there's very efficient radiative cooling, which essentially negates the effect of cosmic ray heating, then the cloud begins to move. And if you're thinking, gee, this is crummy, this is just some numerical noise, it's not. It's actually sound waves bouncing back and forth within the cloud. And so this led us to wonder if there could be cosmic ray driven multi-phase winds. In other words, if cosmic rays could push on dense clouds in this way. Peng also showed this image where you zero in on the front, on the far side that separates the cloud from the hotter intercloud medium. And you can see that the cosmic ray pressure inside the cloud is actually about twice as big as the gas pressure. And then the gas pressure, there's a trade-off. The gas pressure dominates outside the cloud, and the cosmic ray pressure falls off. And Josh modeled the column densities of various ions or ratios of ions in this front and compared it with some data from Bart Wacker from the COS Halo survey. And our model actually does about as well as other models and other best model, and better than some. So we thought this might be promising as a way of explaining some of the ionization of the CGM. Okay, so in a paper that was recently put on the archive, Chad, well, I'll show you a lot of figures from this paper. So the first one is sort of a cautionary note. So a couple of things are different here from what you saw before. For one thing, the cloud is weakly ionized. And so although the gas density in total goes up, the alphane speed in the plasma, which is what's relevant for cosmic ray streaming, actually goes up, even though the bulk alphane speed goes down. And so this is the result of a resolution study where we start with an initial cloud profile and allow a burst of cosmic rays to act on it. And here, the numerical resolution is 2 parsecs, and here it's 1/4 of a parsec. And you can see that the size of this pressure step is a little different. It's actually much bigger if you resolve it enough. And there's also this little thumb here, which is due to cosmic ray heating in this interface. So 1/4 of a parsec is not a physical length, it's a numerical dictated length. And what Chad found is that you need about 10 cells across the interface to get a converged solution for what the change in pressure is and how much heating there is and so on. But there is a bottleneck here. Then we went into 2 dimensions. So the image that Cameron used to advertise my talk with was actually created by Josh Wiener. And here's a comparison of cosmic rays inundating a cloud with 2 different background field strengths, 5 microgauss. So if the field is strong enough, it's able to kind of collimate the cosmic ray flow and not be forced to adjust to it too much. You can see the field lines are mostly pretty straight. The cloud here is getting a little bit stretched out. But if you have a weaker field, like a microgauss, the acoustic forerunner and the cosmic ray pressure expand the field and sort of try to wrap it around the cloud. So you can see that the cosmic rays really want to get past this cloud. So Chad calls it the cosmic ray obstacle course. And later, I'll be talking about the consequences of this drastic change in the magnetic field and even the not so drastic change in this magnetic field, which is not very visible to the eye. So we looked at momentum deposition, cloud acceleration by a 30 megayear burst of cosmic rays. And here's how it depends on field strength. And you can see that there's kind of a sweet spot. If the magnetic field is too low, you don't get too much acceleration. And if it's very high, well, let's see, this is, yeah. So if it's very high, it sort of drops off quickly. You don't really deposit very much momentum. And it turns out that if it's not too big, but not too small, but just right, that's where the maximum occurs. So this is for a fully ionized case and a partially ionized case. Chad also looked at what happens if you have a lot of clumps, not just a single cloud. And you can see, again, bottlenecks vary this cosmic ray front. So there's uniform cosmic ray injection across this boundary. And you can see that how the cosmic rays move and how they distort the field really depends on where the gas density is. Momentum transfer, won't say too much about that. So to cycle back to this question of gamma ray emission for a moment. So on this plot are 2 forms of energy loss. There's collisionless loss, which is the VA.grad P cosmic ray term. And there's the collisional loss, which is what makes gamma rays. And you notice that the solutions are kind of concentrated up here. These are very different transport models. These are different transport models and different clumpiness. So big clumps, little clumps, strong clumps, weak clumps, strong magnetic fields, weak magnetic fields. The total collisional loss always turns out to be about the same. Now, it doesn't always happen in the same place. Sometimes there's more energy lost in the low density gas, sometimes where the cosmic rays are spending most of their time. Sometimes most of the energy loss is in the high density gas, even though the cosmic rays don't spend much time there. But one way or the other, things don't change very much. So we haven't solved this problem of overproduction of gamma rays despite all this work. But I think we have learned some other things. Okay, so let's get back to the basic question of whether bottlenecks actually form. So if cosmic rays are coupled to the ambient medium in the regions between plasma density extrema, in other words, if the self-confinement model still sometimes works, then they heat the gas and they impart momentum volumetrically. They're coupled everywhere. But if they're not coupled, in other words, if there are bottlenecks, then they heat only the interfaces and they accelerate only the clumps, and they have very flat profiles in between the clouds or the clumps. So for the simulation that I showed you, they are so flat So I have a series of emails with Chad with the subject line, how flat? So the cosmic ray gradient length scale, despite the fact that the cloud is only kiloparsecs away from the source, is 100 megaparsecs. The profile goes really, really flat. So do bottlenecks actually form? I mean, we know that diffuse gas in the universe is very clumpy, and magnetic field lines tend to be random. And if bottlenecks form whenever you have some kind of clump along a field line, then I think our whole picture of how cosmic rays propagate has to be revised. So is there anything we might have overlooked that could couple cosmic rays to the thermal gas other than the streaming instability? Well, of course, I wouldn't be asking that question if I didn't have a candidate. So this part of the equation, of the talk, is a little more quantitative with some equations. So let's expand the cosmic ray distribution function. So mu here is the cosine of the pitch. So mu equals 1 is a cosmic ray propagating with velocity entirely along the magnetic field. Mu equals 0, entirely perpendicular. So there's an isotropic part, F0, and then there's a drifting part, and then there's a pressure anisotropy part. And as I said before, the drift anisotropy destabilizes waves of both circular polarizations that co-propagate with the drift. Pressure anisotropy will destabilize waves propagating in both directions, but with opposite circular polarizations. So the wave going one way, one circular polarization will be unstable. The wave going the other way, the other circular polarization will be unstable. In both of these cases, cosmic rays going in each direction have some unstable wave that they can resonate with. And so I have a paper on pressure anisotropy instability, and there's a much earlier paper by Alex Lazarian and Andrei Berezniak from 2006. Okay, so what does pressure anisotropy do? So first of all, after chugging through a lot of kinetic theory, you can write the growth rate of the pressure anisotropy instability in a relatively simple form. This should actually be the absolute value of the pressure anisotropy, so the difference between the pressure in the parallel direction and perpendicular with respect to the magnetic field. Both anisotropies are unstable, although with different circular polarizations. So you can see that if the pressure anisotropy is of order the Alfvén speed over the speed of light, which is a tiny, tiny number, that can be unstable. And for those of you who've worked on the streaming instability, if you just replace this factor here by the ratio of the drift speed to the Alfvén speed, you get the growth rate for the streaming instability. So they're very similar. They both require anisotropies of order the Alfvén speed over the speed of light, which is very small. Okay. So there are plenty of reasons why there are all kinds of pressure fluctuations and so on in the interstellar medium, but cosmic rays can drive their own pressure anisotropy. And here's kind of a close-up of one of Chad's clump simulations that has a fairly weak magnetic field. And you can really see that the field lines, which are very straight here where the cosmic rays haven't reached them yet, they're kind of bulgy and bendy and kinky over here. These are just density contours here. So how does that create pressure anisotropy? It creates pressure anisotropy because charged particles have two so-called adiabatic invariants in a magnetic field that changes slowly. One of them is the magnetic moment, which is basically the magnetic flux through an orbit. And the other is a longitudinal action quantity. And so in a changing magnetic field, so for example, if the magnetic field is getting weaker because it's bulging out, then the magnetic field is getting weaker, so the orbit will get bigger and the perpendicular momentum will get smaller. So a weakening magnetic field tends to create a situation where the parallel pressure is greater than the perpendicular pressure. If the magnetic field were contracting, go the other way. And bending of the field also causes pressure and isotropy. Okay, so in the classic bottleneck picture, the cosmic rays are streaming along the field at the minimum Alfvén speed along the flux tube. So that's not enough to excite the drift and the drift streaming instability, but it will have an effect on the growth rate when combined with pressure and isotropy. So just to get it straight, there are four waves, 2 propagation directions, up and down, and each propagation direction has both circular polarizations. So there are 4 possible waves. And the most unstable wave is the wave in which it's propagating in the same direction as the streaming, even though the streaming is not enough to destabilize it alone. And it's whatever circular polarization is unstable for that particular magnetic field. So that will be the wave with the fastest growth rate. But that wave will not scatter all cosmic rays. In order to have all cosmic rays scattered, the ones going up the field lines and down the field lines, you either have to have waves propagating, linearly polarized waves propagating in both directions, or one circular polarization propagating in one direction, one circular polarization propagating in the other direction, or you can have waves propagating in just one direction, but both polarizations are present. So it's frequently assumed in plasma physics that when you have an instability, it saturates it by modifying the distribution function to bring it back to marginal stability. So if the anisotropy adjusts to stabilize that most unstable wave, all the other waves are damped. You only have one wave, no other waves. So a situation like that is ineffective for scattering the cosmic rays and modifying the distribution function. So with apologies to Jonathan Swift, here is what I currently think. Oops. So without the pressure anisotropy instability, the cosmic rays in a bottleneck would drift at the minimum Alfvén speed along their flux tube. They don't excite the waves and they don't couple to the gas. But the overpressure that accompanies the bottleneck bulges the magnetic field. And it doesn't have to bulge it to an extent that's visible to the naked eye. The ratio of the Alfvén speed to the speed of light, could be 10 to the minus 4, and that's all you need. That's all the bulge you need to start driving an unstable pressure anisotropy. But the pressure anisotropy will be abetted by the subalfvénic drift. It will increase that it will destabilize the wave going in one direction, and it will damp the wave going in the other direction. So there's one unstable wave. And scattering by that most unstable wave, I propose, will reduce the drift and allow the pressure anisotropy, once the drift is reduced, to drive the other circular polarization. And so I think the only situation where you have enough waves to scatter the cosmic rays and they have the same growth rate is when there's no drift. You just have a driftless bottleneck. Now that doesn't mean that the system is completely static, because there's a gas dynamic response. So there's this acoustic pulse or whatever your situation is, but that the cosmic rays are not moving, do not have a bulk drift with respect to the fluid. And so now we can calculate the scattering rate at which the pressure anisotropy is marginally stable. And if you were sort of tentatively she got through the talk without a whole lot of equations. Sorry, I felt I had to do this. So this is a diffusion equation in momentum space, which we can use to estimate how much scattering we need to balance this term, which is driving anisotropy. So we balance this term against this term, balance the warping against the scattering, and what we find is that the scattering frequency is order the speed of light divided by the magnetic gradient length scale, and the mean free path is of order the gradient length scale. So this relatively weak level of scattering, relatively long mean free path, will be enough to restore the coupling to the gas, but it's more diffusive and weaker than the streaming instability. That would be the claim. And so let me summarize this. Okay, so first of all, this classical self-confinement picture breaks down and predicts decoupling when the cosmic ray pressure gradient and the density gradients in the gas are anti-parallel. And at the level of structure in the interstellar medium or CGM or halo, this must happen all the time. And the result is a highly intermittent situation where you have high pressure bottlenecks with very little pressure, essentially no pressure gradient in between the sources and the density maxima, or in between density maxima. And Chad has tested this, accounting for partially ionized clouds, fully ionized clouds, allowing diffusion, not allowing diffusion. And although you require kind of a highly resolved simulation to really do these things accurately, they seem to be very robust. They persist in a clumpy medium, single cloud, whatever. But this picture might be modified by pressure anisotropy instability. So the outcome of the pressure anisotropy instability could be this driftless state in which the scattering mean free path is pretty long. It's of order the magnetic gradient length scale. And I can't help wondering if this could give a better agreement with the gamma ray observations. Could this be a physical mechanism for giving us a large cosmic ray diffusivity? So with that, I will stop and very happy to take questions.
Excellent. Thank you so much, Ellen. That was awesome. We'll give everyone a few minutes to process everything, to go through the Slack discussion. There's been a variety of different questions that were brought up and discussion topics. And we will reconvene here with our whole panel to start addressing some of the questions from the audience. We'll start back at 9:05, so in about 7-8 minutes. So everyone can take a break and catch up on everything, and then we'll start dealing with questions from the audience and our panel.
Thank you.